So, like I said in class, lesson 8.6 is just kind of piggybacking off of lesson 8.5 in the fact that we're still going to be dealing with the same formula. So we're talking about exponential expressions that take this form, okay, y equals a b to the x, and remember that a is our initial value, okay, that's where this exponential graph is going to cross the y-axis. So I'm going to call it the y-intercept. Again, just please understand that we don't actually really call it the y-intercept. Oops, I forgot value. We call it the initial value, okay, in an exponential expression, but it's the same idea. So you can think about it the same way. And then in the b becomes what we call the common ratio. And remember I said this doesn't quite parallel the idea of slope in the same as nicely as the initial value parallels the idea of y-intercept, but the common ratio is going to determine how fast or how slowly our graph rises or declines. So the difference between lesson 8.6 from lesson 8.5 is that in 8.5 we were dealing with exponential growth, okay, so rising from right to left on the graph, just like if you have positive slope in a linear function. In 8.6, we're going to be dealing with declining, okay, from left to right, or decreasing in value, y values from left to right. So this is called exponential decay. It's sort of in this equivalent to the negative slope when we're talking about a linear function. So this problem actually asks you to write the exponential function. Come up with the rule for this exponential function. All right, so the first thing that we want to do, just like when we were dealing with linear functions, is that we want to identify some of our variables. So one of the first things we can identify is our initial value, our a, because our a is going to just be where it crosses the y-axis. Okay, so right here you can see at 0, 1, it's going to cross the y-axis. So our a value in this equation is 1. Okay, our b value we're going to get by figuring out what we're multiplying 25 by to get 5. Okay, so if we're going to multiply 25 by something and get out 5, the only thing that will work, it would be the fraction 1/5. Okay, if you multiply 25 by 1/5, you're going to get 5, which is what we want. Okay, a good thing to do, though, is to not just take the very first thing that works. Check it on the next value. Check 5. If you multiply 5 by 1/5, do you get 1? And yes, the answer is yes. Same thing here. So it works in this step. If you go from 1 to 1/5, 1 times 1/5 is 1/5. 1/5 right here times 1/5 again would give you 1/25. So it does work. The common ratio, the thing you're multiplying each of those y's by, is 1/5. So that means your b is 1/5. So now from there, that's very easy to write the function. Okay, so remember, we're going to, just like when we write an equation out, a linear equation out in y equals mx plus b form, we leave the y just as y. Our a is 1, and our b is 1/5. So I'm going to put that in parentheses because the whole thing is going to be raised to the x power. So we end up with y equals 1 times 1/5 x. If we simplify that, I don't know what's happening here. Okay, if we simplify that, we'll just get y equals 1/5 x. Now number 2, I'm not going to spend a whole lot of time on this one. I went ahead and plotted the points for you on this graph. So those are the points. And to show you that this is not exponential. This does not have any kind of correlation. Okay, so there are going to be sometimes when they ask you, looking at the coordinate pairs, whether it's exponential or not. The way you can tell is to see if there's anything you can multiply to get the next one out. So if there's nothing I can multiply 1 by to get 4 out, and there's nothing I can multiply 4 by and get 7 out. So because those steps, these don't grow exponentially by multiplying by the same thing, it doesn't work. Now, don't get confused by this, though. You could add 3 here, and add 3 here, and add 3 at each of these steps, and get the next consecutive number out. But we're not talking about adding. If it's exponential, we are only talking about multiplying. You can only multiply in between these steps. If there's nothing you can multiply in between steps to get the next consecutive number, then it is not exponential. You don't actually even have to graph it. I just graphed it for you so you could actually visually see that it's not exponential, but that you don't have to graph it. You can tell just by analyzing the y's. So looking at number 3, they ask you to graph the function and identify its domain and range. I know there was some confusion in class. You guys mentioned that it was a little bit confusing how to get the x and y values. So let me just go through it again. I already wrote out the table over here. Okay, so you're going to write out a table just like you would if you were graphing anything, and choose -1, 0, and 1 for your x values on these exponential functions. They work out really nicely and they give you enough information to get a nice curved line usually. Okay, so all I'm doing is plugging in those x's in here as the exponent. So I wrote it out over here on the right. If you take y equals 1 over 12 and you plug in for x that -1, I'm getting that -1 over here out of my table. If I raise it to the -1 power, remember when I distribute out that -1, I'm going to distribute it to the 1 on the top, and I'm going to distribute it to the 12 on the bottom. So what that tells me is that I have to take the reciprocal of both of them. I need to put the 12 in the numerator, the 1 would go in the denominator, but obviously I can just call that 12. 12 over 1 is 12. So that becomes my y value. If I raise 1/12 to the 0 power, I'm just going to get 1. And then obviously if I raise 1/12 to the first power, I'm just going to get the same value back out. Okay, so those make it nice and easy to find your values. Okay, so when you plot those points, they should look like the points there that I've plotted on the graph, and then you're going to draw that nice curved line through the 3 points, remembering not to cross the x-axis. Okay, so the domain on this, these are your x values. They're all reals, all real numbers. So any x can go into here. That's what that means. Your range, if you notice, you are above the x-axis. So if you're above the x-axis, all the y values, which is your range, are going to be positive. So you're going to write all positive real numbers. Okay, so here on number 6, I picked this one to do because it has that negative sign in front of the 1/8. Okay, so remember, that means that if this is your formula for exponents and for exponential functions, this tells you that your a is -1. Okay, and the other one, it was +1 because there was nothing recorded there. That negative sign there really means -1. So you know that your a in this equation, this function, is -1. That means that you would expect it to cross this y-axis down here. Okay, in the range where you've got all negative numbers. Okay, so hopefully that's what ends up happening here. If you come over here, I made my table. I picked -1, 0, and 1 for the x values, and I just went ahead and already wrote out that function and plugged in -1, 0, and 1 in for that exponent. Okay, so I wrote those over here on the right-hand side. This gets a little bit tricky, so you've got to pay attention when you have a negative sign there. Okay, so when you've got that negative sign out in front, we're going to leave that alone for just a minute, and we're going to distribute that exponent of -1 to both the numerator and denominator. Okay, and what that's going to require you to do then is to reciprocate both of those. You're going to end up with the 8 up in the numerator, that 1 in the denominator, but the 1 in the denominator doesn't need to be there, so we're just going to call this -8. All right. Same thing here. We're going to leave that negative sign out there. We're going to leave it alone for a minute. It is not inside the parentheses. So it is not being raised to the 0 power. But the 1/8, both the numerator and denominator are being raised to the 0 power. Well, you know anything raised to the 0 power is 1. Okay, so that's going to mean that you've got the opposite of 1 here. And then on the bottom, the last one, you have that negative sign, leave it out there. It's not being raised to the 1 power, but the 1/8 is. So we're just going to end up with that number itself. We're going to end up with 1/8 again, and then you take the opposite of that. So the value here is 1/8. So I'm just going to plug those numbers in over here. When x is -1, y is -8. When x is 0, y is -1. When x is 1, y is -1/8. Okay, and I plotted the points in red and then graphed the line in blue, hoping that you could still see those points. So your whole graph is going to be in the range where the y's are negative. So this makes your domain, still your domain is all reals. Okay. Your range, though, now you're underneath that x-axis. You're in to where all the y's are negative. So you're going to say all negative real numbers. Okay, and these last 3 problems that we're going to do, they're asking you to graph the function that's given and then compare it to the graph of y equals 1/8 x. I have put y equals 1/8 x over here, and the table for it is below, and I went ahead and graphed it. Okay, so all of y equals 1/8 x is in green. If we do the y equals 2 times 1/8 x, okay, we can see that our a now has changed from 1 to 2. Okay, so if I plug in this -1 here into my x up here, I will get 2 times the 8. Okay, if I put -1 in for x, I'm going to have to reciprocate my 1/8. So I'll end up with 8 right here, times that 2, it'll give me 16. Okay, if I put 0 in for x, then I'm going to raise that 1/8 to 1. I'm sorry, 1/8 raised to the 0 is going to give you 1. 1 times this 2 right here gives you 2. All right, and then if I plug into here the 1, x is 1, I'm going to get 1/8 out. If I have 1/8 times this 2 again, I'm going to get 2/8, or if you reduce it, 1/4. Okay? Okay, so when you graph it, it will look like the purple line. You can see if you're comparing the purple line to the green line, which is what they asked us to do, you can see that it's just shifted up 1 unit. That purple line is crossing at y of 2 instead of y of 1. So when that happens, when the graph is actually moved up, this is same as last section. It is called vertical stretch. You are vertically stretching the graph up. Okay, on the next one, you can see that I've already graphed the y equals 1/8 x in green again. It's the same one from the previous graph. This is the one we're comparing this new function to, this y equals -1/8 raised to the x. So if I plug my -1 in here to the x, I'm going to end up reciprocating the fraction to give me 8, and I want the opposite of that. Okay, that's what this indicates right here. So I'm going to get -8 out of that. If I raise that x to the 0 power, okay, now instead of having 8 here, I'm just going to have 1, but I still have to go back to this negative sign here and say -1. And then if I put 1 in for x, I will get 1/8 back out, but again, I've got to remember this negative sign in front of it, so I'll get -1/8. So when I plot the points and graph it in, put the curved line in, you can see that they have the same shape. It's just that one is in the positive side of the the graph, and the other's in the negative. So it is reflected over this right here. It's a mirror image. That thing that I just drew in red is the x-axis. So we call this reflection in the x-axis. Okay, same idea as 8.6. I'm sorry, 8.5. It's just now we're dealing with exponential decay functions, ones that are decreasing left to right instead of increasing left to right. Okay, and finally, number 14, if I plug -1 in up here to my x, I will have to reciprocate, which will give me 8 here. 8 times this 1/4 will give you a y of 2. If I plug in 0 for x, I'm going to get a 1 here instead of the 8. 1 times 1/4 gives you 1/4. Okay, I'm just multiplying that 1 by the 1/4 here. And then if I plug in 1 for x, I'm of course going to get 1/8 back out. 1/8 times 1/4 is 1/32. Okay, and this one's a little harder to see, but if you compare the purple to the green, you can see it's closer to the x-axis. It gets moved down instead of up, so we call that vertical shrink.